the literature, you will find a lot of uh, methods or tools which can be used for optimization. In fact, when you start optimization, you have to conduct so many experiments and you have to apply some technique to find out the optimized value of the input parameters. Basically, what we do in any optimization problem, we define some input parameters to get the desired output, either to minimize something or to maximize something. And based on our decision on the input parameters and output parameters, we apply a method, and by using that method, we get the desired output. Either this can be a single objective or this can be a multi-objective. In a single objective, what we do is that we optimize only one output parameter or the response, we call it. And a multi-objective, simultaneously, we optimize several objectives or several parameter output factors we optimize. Okay. Let us say one such method or one example of this, we are having the electrochemical machining. How we can optimize the parameters, input parameters like current, voltage, etc. to optimize the metal removal rate or MRR, or the DOC, and on the surface roughness, etc. How we can optimize that one, that we will see through this one. Taguchi's method is such a method which can be used for optimization. And Taguchi, as you know, that he is a Japanese engineer who defined the quality in his own way. Generally, how do you define quality? We define our quality based on the customer satisfaction, whether this is meeting to the functions, desired functions, or it is up to the level we expect. That is the traditional way of defining quality. Okay. And no quality loss is there if the product is within specifications. It means if you are going for the upper control limit and the lower control limit, we are having the tolerance band. Within that tolerance band, if we find something, we say that there is no loss because it is within the tolerance band. But Taguchi defined it in a different way. Okay. And as per Taguchi, quality is when the process output is at the target, not below that or not above that, it is at the target. And he defines two limits, like the lower specification limit and the upper specification limits. If within these limits also you get the target or you get the output, then although there are some losses. There are losses in the quality because it is not directly achieving the target, rather it is below that or above that. So you are having some loss within that, although it is within the control limit. But according to traditional quality, if it is in the control limit, then we can say this is okay, there is no loss. But in fact, there is some loss because this is not meeting the target. Okay. And this is the definition, or this how quality is defined by Taguchi. And if there is larger deviation, it means that there is larger loss, if at all, or although this is within the control limit. Now, according to Taguchi, there is an ideal quality, and that refers to a reference point or a target value for determining the quality level of a product or service. That is the target level, as you have seen in the previous one. And the ideal quality is delivered if a product or a service performs its intended function throughout its projected life under reasonable conditions. Okay, so we can say this is working within that particular range and for the limit of the period that we have defined. And this ideal quality, this is a function of customer perceptions and satisfaction. You know, this perception and satisfaction both are qualitative term, and in this qualitative term, it has to be converted to some quantitative term so that you can go for optimization of the parameters. Okay, you have to convert it to some quantitative terms. Okay, how this is converted, we will see. Now, as you have understood that quality is according to Taguchi to meeting the target, and in any process, in any manufacturing system, either it is a service or this is a product, there are some inputs, and when this is subjected to some process, you get some output. This is the traditional manufacturing process. Under ideal condition, there are no noise. There are different control factors are there. There are no noise, and this falls within the lower specification limit and the upper specification limit. Within this limit, this can remain, and these are the allowable. You can allow up to this one. These are the tolerance band. Now, if you put noise to that, now what is the meaning of this noise? We'll see some noise factors are there. In any system, there are some noise factors, there are some process, there are some mismanagement, maybe human error, maybe the error of the system, maybe error of the workstation. So there are some noise. And when you get some noise, now you can see this is crossing the lower control limit, a lower specification limit, and the upper specification limit, and you get more defects. You get more defects. And when you get the noise factor, you see the noise factor, the control factors, input and output. If you see the previous diagram that was out of control, now you can see this. According to Taguchi, if at all there are some noise, but still it should be within the limits, lower specification limit or the upper specification limit. It should be within that. Like a goal post, if you score a goal, if you wish to score a goal, then you have to put it inside within the goal. Okay. So similarly, if at all there are some noise will be obviously there in any system, and with this noise, you have to reduce the noise so that it will be within that lower specification limit or upper specification limit. Within that, you can imagine that there is a goalpost, and you are minimizing the noise or the noise factors, you are reducing the noise factors, and you have to keep within these two limits. This is the basic philosophy of Taguchi, that you are working on the noise. You are working on the noise, and if you reduce the noise or if you reduce the errors, then obviously your control will be better or quality will be better. That is the basic philosophy of Taguchi. So now, what is this Taguchi design of experiments? This Taguchi method, which is standardized approach for determining the best combination of inputs to produce a product or a service, and this is accomplished through the design of experiment or the DOE. It is a basis for determining the functional relationship between controllable product service design factors and the outcome of the process. This is in general. What we see is that this is the input, or this is the input factors or input parameters relations with the outcomes or the responses. It is a method for adjusting the mean of a process by optimizing the control variables. You define the control variables, and basically what is done, this approach, there are four perspectives. One is the robust design, a concept design, a parameter design, and the tolerance design. And when these four are combined, it is constitute the Taguchi approach, or this constitute the Taguchi method. This is the approach of the Taguchi design of experiment. Now, what is the robust design? That robust design, that you have to make it defect-free and high quality. The defect-free and high quality. And this Taguchi approach for creating robust design is through three-step method consisting of concept design, parameter design, and tolerance design. Okay. What is the concept design? This is the process of examining the competing technology to produce a product. to produce the desired output. Okay. So in the concept, you have to go for different concepts, different alternatives, study the alternative, and ultimately you for just conversion one alternative or one method or one technology so that can be applied. That is the concept. And this concept vision includes the process technology choices and process design choices. The design and process technology both, whether in a process, whether this will be automatic, semi-automatic, automated, semi-automated, and in the design, whether designing of the layout, design of all other things, the human behavior, everything, it comes under the process and the design choices. So this is the concept design. Means you see in one sentence, I can say that this is the conceptualization of the product and process and the design of the product and the process. That is the first one, that is the concept design. Then parameter design, this refers to the selection of the control factors and either the level or the range of each factor that is to be controlled. Means basically these are the input parameters which are required to be controlled, Okay. And these control factors are those variables in a process that management can manipulate, the input parameters which the management can manipulate or the user can manipulate these, not the user, the management or that can manipulate. And control factors do not affect production cost. Cost is depending upon this. When you say the production cost, it is basically the raw material cost and all other costs related to the process. In terms of time of production. In terms of time of production, the time of production is converted to cost unit and you find out the cost. So these input parameters, these do not affect the production cost. The optimal levels are the targets or the measurement of our performance. What is our desired performance? Or what are the performance outputs that we require? That is to be defined in the parameter design. The goal is to find the most efficient process and service design. You have to find out this, you have to think over this. The goal is to find out the most efficient process and service design. And these parameters, which one to be selected, which one to be considered. This can be determined through various experiments, and also through the various brainstorming sessions. We can find out these parameters. Now next is tolerance design. This deals with the developing of the specification limit, the upper specification limit and the lower specification limit. And this occurs after parameter design has been used to reduce the variation and the resulting improvement has been insufficient. Okay. So you have to, based on experiments, you have to define the upper control limit or the upper specification limit and the lower control limit or the lower specification limit. Okay. And this very often results in an increase in the production cost. When you limit the tolerance, the cost defectives will be more, and hence you will get a lot of defects or the defective items, and hence the cost will be increased. So out of these four considerations, Taguchi method mainly focuses on the parameter design, Hence, here also we will study how we can design the parameter with the design of experiment using the philosophy of Taguchi. Now, when this Taguchi philosophy or Taguchi methodology can be applied? When you have got large number of factors, there you can use the Taguchi methodology, and then time and cost of experimentation has to be lowered or can be lowered. Okay, you have to reduce the time and the cost of experimentation. So suppose there are so many factors are there, and for each individual, if you go for the so many experiments, the cost of the experimentation will be very high. Hence, you have to reduce the number. To reduce the number of experiments, you have to adopt the Taguchi philosophy. And in cases where the number of control factors are more than the number of noise factors, in that case, this is applicable because there is a better chance of finding a factor which will help in reducing the noise. In reducing the noise. And the product and process under design is extremely critical, and in no condition shall the process deviate from the target. There you have to apply this Taguchi method. And when the design objective is not just to attain the nominal best for the response, but to attain best relationship between output response and the input signal factor, there you have to adopt this Taguchi methodology. But most importantly, what is required is that the Taguchi method is applied generally when you have to, the main objective here, why we use practically is that we wish to reduce the number of experiments. We need not conduct the complete experiment, or the number of experiments are reduced in this case. Okay. And it defines a function that is called the quality loss function. That is the quality loss function. Now we can look at this diagram. In this diagram, you can see that at the middle, this is called a step function. This is a target is defined. The target is defined, and here there is upper specification limit and the lower specification limit. Lower specification limit and the lower specification limit. Suppose one observation, a point A is closer to the upper specification limit without being at the target. This is not at the target, rather this is at the at some other point which is nearer to the upper specification limit. What you understand from this? We understand that this is within the control, this is within the control, but and this is a good part or a good product or a good process. But still, as this is not meeting the target, it is incurring some loss. Okay, and that is a potential loss to the society. And according to Taguchi, he calls it that this is the potential loss to the society, because this is not achieving the target, not achieving to the point. There are still some error, although it is within the control limit. Okay. So, and Taguchi identifies these losses to society not only in terms of rejection, scrap or rework, but also in terms of pollution that is added to the environment, and product that wear out too quickly, or other negative effects that occur. For everything, for rejection, scrap, rework, or pollution, product wear and tear, this cost a lot. Okay, and those are the losses. Those are the noises, you can see. Those are the loss to the society or loss to the system, and those are the, you can say, the, and you have to, if you can reduce this one, means you are reducing the noise. If you are reducing these, means you are reducing the noise. Okay. So continue with this quality loss function. To quantify these loss, you can see this is lower specification limit and upper specification limit, and there is a target. The target is 6. Let us say for this one, target of 6 results in some loss to the company. Okay, and this is defined by a function that is called the quadratic loss function. This is quadratic loss function. The quality loss function focuses on economic and societal penalties incurred as a result of purchasing a non-conforming product. Although this is confirming the things, but if you go for a non-conforming product, then you are incurring a loss, or you are getting a loss. And these losses may include the maintenance cost, failure cost, ill effects to the environment, such as pollution, excessive cost of operating the product, and such things. Okay. And this quadratic loss function is being defined as this one, that this is a quadratic function, that loss y is equal to k into y minus m square. The k is a constant dependent by a by d square. A is the cost of corrective action, and is the value of the process. This is the constant k. This is empirically related. And y minus m, y is the measurement of the unit, and m is the target value, how it is deviating from the target value when this is squared, this becomes positive. And so this is having quadratic equation. This is quadratic equation or the second degree equation. And this is the loss function. This is defined as the loss function. What is the objective of the loss function? The function drives the objective of the Taguchi design, which is to design a process that is not just complying to the customer satisfaction, but also aligned to the target. Not only the customer satisfaction. Now we here give a reasonable conclusion that according to Taguchi, we are not only achieving the target, but at the same time, not only you are getting the customer satisfaction, but also we are achieving the target. We are achieving the target, or it is aligned with the target. Now, based on this philosophy, now see how this can be applied to a system. There are different signals, and we are getting noise. Now you know what are the noise, and there is a ratio that is called the signal to noise ratio. This is a logarithmic function which can also be defined as an inverse of variance. This is now generally what we need in any optimization problem. Having theory, we go for the variance and all those things, but this is inverse of variance. In this case, the numerator is the signal and n is the noise. Noise is in the denominator. So when the noise is decreased, what happens? The ratio increases. The ratio increases. So it is our aim to maximize the SN ratio or signal to noise ratio. Okay. And what are the control factors of the signals? The signals are the control factors which the design and process parameter that can be controlled, that is within our control, that is the input parameters that can be controlled. Those are the signals. And the noises are, we cannot control, those are uncontrollable. Those are uncontrollable during the experimentation, but noise factors cannot be controlled during production of product. This can be controlled during the experiment. When we go for experiment, we can control this noise. Okay. So product with this goal, that is higher SN ratio, will deliver more consistent performance in the extreme condition. So we use the signal to noise ratio. Ultimate aim is to reduce the noise, and hence the signal to noise ratio, the higher value will yield a better performance in terms of the output. That should be our ultimate aim. You can see there are different functions, like this is defined. Generally, there are three functions are used. First one is the larger the better. Larger the better. For example, you need the fuel efficiency, strength, tensile strength, compressive strength, adhesive strength, corrosion resistance. These are the required in higher. So in this case, we define a lower specification limit. Within or below that, these are rejected. Below that, these are rejected, and we accept other things above that one, above the lower specification limit. This is called the philosophy of larger the better. Another one is, this is the equation given by larger the better. Another one is the smaller the better. For example, the wear of a automobile tire, pollution, smaller the better. Defective, smaller the better. Sinkage, radiation, this is smaller the better. So we go for the smaller the better, and this is being the equation being depend. This is the equation of this smaller the better. You can study the graph. You can study the graph. This is the inverse of this one. This is the inverse of the first one. Now, nominal the best. Actually, this is the, we have to achieve the target. We have to achieve the target within these control limits. Within these control limits, this is the basic equation. This is nominal the best. But while we are going for this one, we have got different control factors or different input parameters. Now let us suppose for a machining problem, in a machining problem, MRR required is high, but the surface requirement is low. So in one case, we follow that larger is better. MRR, that is larger is better. And in the surface roughness, we need the smaller is better. That is what we need in case of the second one. Okay. So these are the different functions we will use while optimizing the process. And how to choose this one? Smaller the better. This minimize the responses. This minimize the responses. Larger the better, this maximize the response. And nominal the better, this is target the response, and you want to base the signal to noise ratio on means and standard deviations. Means this is directly moving to the target. This is directly achieving the target. So when there is a minimization issue, then you have to refer to smaller the better. And when there is you need to maximize, then you have to go for the larger the better. Okay. Now, what are the advantages of choosing this one? The advantage is that the response varies related to the nominal or target value under different noise conditions. Okay, not the control conditions. And the validate and prediction of optimum performance signal to noise results transformed into a logarithmic scale. Means if at all there is some non-linearity, this can make this behavior a linear one. This is the main advantage of using this signal to noise ratio. Now, different steps of Taguchi method or methodology, how to optimize issue. Now, this is the 8-step method. In this 8-step method, first step is to identify the main function, its effects, rather side effects, and different failure mode. This is the first one. Identify the noise factors, testing conditions, and quality characteristic. Identify the objective. Identify the control factors and their levels, the input factors or input parameters and their levels. Select a suitable orthogonal array, what are the orthogonal array we'll see, and construct the matrix. Conduct the experiment. You go for the conduct the experiment with the help of some the setup. Then examine the data and predict the optimum control factors levels and its performance. And after getting the optimal parameter setting, you have to go for one experiment that is called the confirmatory test or the confirm test. You have to conduct the panel verification. Now, if you define it in a flowchart, it is initialize the problem with selection of different parameters, orthogonal array, and the fitness function. Then design the input parameters using the orthogonal array. Conduct the experiment and make a response table. Identify the level of values and conduct confirmation test. Termination criteria, if termination criteria is met, otherwise you can go for redesign them, or you can go for optimization, or you can go for redesign the orthogonal arrays. So these are mainly the 8 methods or 8 steps in the Taguchi methodology. Now we have taken one, let us say one example where it is an electrochemical machining or reasoning process, ECM process. And the side effects are the metal invalid surface finish, surface roughness, and radius overcut or ROC. And it lists down all the factors that will affect or influence the machining parameters. There are 2 ways. This one is very important. You have to identify, or you have to find out, or you have to know what you are going to do. What should be the input parameters, and what should be the range, or what should be the levels of those input parameters, and what are the objectives to be optimized. You can make it, or you can do it in 2 ways. One by brainstorming session, and this you can take different ideas, knowledge from various literature, from the experienced operator or skilled operator, and from previous data of experimentation. So based on this, you can have this session, and if this happens, then what will be the consequence? You have to go for a lot of brainstorming sessions with other people also. You can discuss this one, and you can find out what are the objectives and what are the control factors or what are the input parameters. Or you can go through one fishbone diagram. Okay. Now you can see that The example we are going to discuss is that is the electrochemical vessel. If you select the uh, performance criteria as MRR, performance criteria as MRR, the metal removal rate, okay, and the accuracy, surface finish, repeatability, this one, then what are the input? This is the what are the power supply, what are the mechanical inputs, what are the electrolytes, what is the macro tool, what's the insulation, and if you go for the power supply, what's the frequency, voltage, and current, what is the pulse period and duty ratio, what is the feed rate, okay, and mechanically, you can what are the deflection, rigidity. Out of these so many things, you have to study that which factor or which parameter is affecting most, which parameters affecting most, and also you can from this you can find out what are the noises or what are the noise factors which are not under control, but except during the experiments in the laboratories. Okay. So either from brainstorming session, okay, that is a qualitative method, and from the fishbone diagram, this is also a qualitative method. You can find out what are the control parameters or the control factors or the input parameters and the response or of the desired performance is required. This you have to find out from these two. So here we take this for this electrochemical measuring. I've taken this voltage, feed rate, the concentration of the electrolyte, and electron content. This A, B, C, D. There are these four input parameters, and we have defined the range. We define the range that is from 1 to 3 or 3 levels. Means it is voltage is varying from 12 volts to 20 volts. Feed rate is from 0.2 to 1. Similarly, electrical concentration 10 to 30, like that we define the level or define the range, and within that range we define 3 levels. We define 3 levels: level 1, level 2, level 3. These are the input parameter settings. These are the input parameter settings we define here. And now to choose an orthogonal array. What is the orthogonal array? Orthogonal array they are used to represent the controllable factors and noise factors in a robust design. Robust design, that is parametric design, and all those four, the three we started that part is a robust design, that is zero defect design. And optimal levels of these factors are to be achieved, which will maximize the response and minimize the effect of noise factors. This is where we go for this orthogonal arrays. Traditionally, the orthogonal array is given by this expression, that is ln s to the power k, where s is the number of levels for each factor. Number of levels for each factor. And k is the maximum number of factors. This is the k is the maximum number of factors. And n is the number of trials. How many trials you are having or how many experiments you are conducting. This is the traditional way of representing the orthogonal array. So these are, let us say, if you are going for 2 to the power k, 2 to the power 3 factorial design, then this table gives the design table, that is minus R3. This is 2 to the power 3, 0, 0, 0, 1, 0, 0, 0, 1, 0, like this. We can cover this the experimentation, or this is the factorial design. This is the 2 to the power 3 factorial design. In fact, there are other tables or orthogonal arrays which can be used for different experimentation or different methods. You can see some of the arrays are L4, L8. In the L4, we are having 4 runs, and maximum factors that can be considered is 3. And this is based for 2 level, and for 3 level we can use the L9, L18, L27. Most commonly use L9 and L27. All these are L27 is having, you can have 27 experimentation or 27 runs. L81 you can have 81 runs, and this can get either 2 level or 3 level as defined here. Then you have to select one orthogonal array. One orthogonal array based on your requirement. So here we choose because we have got 3 level, so we have chosen the L27 arrays in this. We'll see this from later. Okay. And how to go for the test strategy? Test strategy means how do you have to go? Either you have to go for a full factorial design, or you have to go for a fractional factorial design. Full factorial means you have to conduct all the experiments or all the combinations. And so in 2 level full factorial design, you have to conduct only 2 level vectors. The number of runs necessary for a 2 level is 2 to the power 2 to the power k, where k is the number of vectors. Okay. So either you can go for the full factor. This is applicable when the level is less or the parameters are less. You can go for the full factorial design. Otherwise, you can to reduce the objective is to reduce the number of experiments. You can adopt the fractional factorial design. You can just go for less number of experimentation, then you can go for the fractional factorial design. Okay. And based on this, here we have chosen the parameter like current, voltage, and concentration, and all those. What is our objective? And your response, our output response, our response parameters are, that is MRR, surface roughness, and the radial overcut of the ROC. Now see how we can apply the Taguchi method to this one. And based on this Taguchi method, how we can optimize in a single optimization, and then you can move on to the multi-objective system. Okay, so in the philosophy or the method which we are presently discussing is that first we will go for the single objective optimization, then we will combine this with the utility method, and then we will go for the multi-objective optimization. So here, with the help of this Taguchi method, Taguchi design of experiment, we have defined our input parameters. We have defined our performance. There are 4 input parameters and 3 performance measures, and we can optimize each of these one by utilizing one orthogonal array. Now, this is the result that you have got from the experimentation. Okay. Now you can see that there are 27 runs. We have adopted L27 orthogonal array. There are 4 input parameters as defined earlier: A, B, C, D, and the performance are MRR, SR. That is the MRR is the material removal rate. SR is the surface roughness, and that is the radial overcut. And we've got the mean standard deviation as well as this SN ratio for that. SN ratio. This is got from the experimentation. Then, with the help of some software, data analysis software such as Minitype, we get all these things. We got this one. Now, how to analyze this and how to arrive at a solution after getting this one from the simulation. In order to arrive this, now you can see we can get different plots and different levels. For this MRR, our condition is that here the larger the better. MRR should be larger. Metal removal rate should be larger. Now, from the table, you can see that this MRR level, there are 3 levels, level 1, 2, 3. Now, for parameter A, the maximum value is 0.661. For parameter B, this is 0.722. For parameter C, this is 0.612. And for parameter 1, this is 0.596. 0.596. Yeah. And if you see the main effect plot, what is the effect of this one? On means of the data means of the noise ratio. Then here, objective is that the SN ratio should be higher. So this is higher in this case. This is number 3 point. This is number 3. This is number 3, and this is number 1. These are higher. And when you get this one, here these are ranked that this is having maximum effect. Factor B, parameter B is having maximum effect on the, or the significant effect on the performance output. Similarly, this is having rank 2 in terms of the effect and in terms of the effect on the performance output. Okay. So this is how this is affecting the MRR. We have adopted N27, that orthogonal array, and with an objective that larger the better. Larger the better. With the help of the software, you can get this. Okay. Now, what is the optimal parameter setting? The optimal parameter setting is that here A3 that is higher, B3 higher, C3 higher, D1 is higher. So we add this one minus 3 times the mean value, calculate the mean value, and because there are 3 levels of 3 performance outputs is detected. So this is, we are getting the MRR, optimal MRR is 0.99166. From this one we are getting this. Okay. So we have optimized the MRR or the material removal rate based on one L27 orthogonal array and based on a philosophy of larger the better, and from the calculation we are optimizing this one. But by this setting, this A3, B3, C3, D1, the other things may not be achieved. The other things may not be achieved means we may not be able to minimize the surface roughness. We may not be able to minimize the overcut. Okay, but this setting, this parameter setting, this parameter level setting is helpful for the material removal rate. Now for the second one, the surface roughness, we need smaller surface roughness. It should be less. So in this case, it is smaller the better. It is smaller the better. Hence, we choose based on the parameter level which one is yielding or which one is giving the smallest or the minimum value. Here this is minimum, here this is minimum, this is minimum, and this one is minimum. And we get this different ranking. We get this different ranking. And here we can see that the optimum value we will get that when A is set to level 2, B is set to level 3, C is set to level 3, and D is set to level 1. And from usual calculation, you can get the optimized value. Now, if you see, the previous setup was different, the previous setting was different, that was for the MRR, and this is for the surface roughness. This is different from the previous one. And for the same experiment, you can make it, but here, what you are doing, you are we are getting this optimization as our single objective. In any process, let us say 3 parameters, 3 performance are there, MRR, SR, and this DOC. We are focusing on, if you focus on one, then you should adopt the single objective method. You have to go for the single objective. Okay. Similarly, you can go for the radial overcut. In this radial overcut, we have again got a different setting, that is A is set to 1, B is set to level 3, C is set to level 1, and D is set to level 3. So in this case, we are getting the optimal setting like this one. This is the optimal setting with the help of this equation, this method, this equation. We are getting this one. So what we got here is that we conducted some experiments based on Taguchi philosophy, adopted one orthogonal array, adopted the policy of this, either the smaller the better or the larger the better, and we could be able to optimize the individual parameters, the individual performance output in terms of the input parameter, in terms of the input parameter. Okay, but we are not able to find out the overall or the holistic or the total optimization. Also, based on these input parameters, that simultaneously all the things should be optimized. It means the MRR should be increased, then DOC should be reduced, and the this SR should be reduced. We are not getting that one. That when you just go for a single modification in this or single augmentation of this method, we can, that is the utility theory. If you go for utility theory, based on this Taguchi, and if you add this Taguchi and utility, then you will get the multi-objective decision. Like you will get the multi-objective decision. Okay. What is this multi-objective decision? Or what is this utility? This utility represents the satisfaction that comes that consumer receive for choosing and consuming a product process of surrogate. For example, you are supposed to purchase a car, you are going for a car. But these are the things we'll consider, that is the fuel efficiency, safety features, riding comfort, space, how much money you are having, there are different attributes are there, and you go for the decision making. So this is a collective decision, this is a several objectives you put together and get a decision. So this is called the utility. It means all these parameters are giving some weightages, or they will calculate the individual utility, make the system a non-dimensional one, and add up these utilities so that you will get an overall utility, which will simultaneously improve or which will simultaneously optimize all the input parameters. This is the objective. Okay. So here we are finding out the overall utility. Okay. The satisfaction provided by all attributes of the product or a process to decision maker. And it's known as the utility of the product or process. This is the overall utility. But in this case, we'll find out the individual utility, and then we add up these things with some weightages so that we will get the overall utility. Okay. And this is on logarithmic scale. This is to make it a linear one. Now, here, this one, the overall utility of a product or a process, okay, can be represented by a unified composite index, which is the sum of individual utilities, as I told, of various quality characteristics of the product or the process. The best choice provides the best satisfaction, which refer to the maximization of the utility. And this unified composite index is to be optimized by using the Taguchi approach or the Taguchi method. So this is, as I have told, this is single response, but utility concept, you can make it a multi-response problem. This is the different step. There were 8 steps. Here you can see the first one is about Taguchi method. Experiment design and execution, SN ratio calculation, multi-response, then this is the utility function. Here this is predicted optimum value of each response. Then you go for the preference number calculations, or preference number or utility index, you can say. You calculate one utility index. Then assign the weight to the each response. Means that here there are three responses are there. And from the brainstorming session or from your own by judicious analysis, you can say that I will give out of 1.42 MRR, 0.32 SR and 0.32 DOC. Or you can give equal weightage to all the factors. Okay. Then equal to all the response here. After assigning the weights, you calculate the overall utility. Calculate the overall utility, and what you get out of multiple responses, you get a single response. You get a single response, not in terms of any factors or input parameters, rather in terms of the utility parameters. Only one parameter, you get a single response, and that is the optimal factor levels, and that determines the optimal factor levels. Okay. So in this case, how this is done, you can see these are some of the mathematical expression that these are the utility of the system, and this is a function of each individual utility, and the overall utility is calculated by summing this one. By summing this one, this is the overall utility. And this is a individual characteristic. You have to calculate 2 things. That you have to calculate, if you wish to calculate yj is equal to z to log yj minus yj by yj bar. This expression is important because from this expression you calculate the individual utility. You calculate the individual utility. Okay, what is this utility? That you have to find out the value of z, and you have to find out the value of y bar, so that you can find out the utility of yj. Yj refers to the value of y for the jth attribute. Okay. What is y bar? Y bar is the worst value. Y bar the worst value means when this is the minimization problem, you can take the maximum one, or you can put a limit to that one. How will so that will the example will see this one. And this is when this is smaller, the better. So what you need the smallest one. So what will be the worst one? The largest one will be the worst one. Okay. So the maximum value amongst the performance of attribute, you can say that is the worst value. That is the worst value. Okay. So in case of this smaller the better, the maximum value is called the worst value. And in the same logic, in case of the larger the better concept, your worst value will be the minimum value. You need larger values, but you are getting the minimum values. You are getting the minimum values. Okay. So lower values are supposed to be the worst value. Okay. This you have to get from the experimentation that you have got. That is y bar. That you have to find out what is the yz bar is. That is the worst value. Now, how to calculate z? You have to calculate z by this way. That if you see the previous one, that there are two arbitrary values, either 0 or 9. Okay. These are assigned to the just acceptable value, the worst value, and the most acceptable value, the best value. The best value. Suppose in any experimentation, you got the MRR is the highest one. MRR is the highest one. So if you put the y bar in the numerator, that is the optimized value. That is the optimized value, the highest value, and that is the most acceptable value. And hence you have to put in number 9 there. If you see the previous slide, let us see which one. This slide here, if you take it to the other side, then this is yj. This is a variable you can see. In place of yj, if you put the largest value, then that factor will be 9. And if you put the lowest value, that factor will be 0. That factor will be 0. So if you make it 9 here, then z value will be log, that's the maximum value, by the worst value. By the worst value, you can find out the z value. How this is found out, you see. Evaluation of this constant. If you refer to the table, the value of MRR is 0.2 gram per minute. That's the minimum value. Since all MRR values are greater than 0.2, that's the minimum value. So, and the maximum, what is the maximum value? Maximum value is the 0.99166. So that's the most acceptable value. And the best optimum value, okay, here you have to either put a binary number 0 or 9. That 0 or 9 you have to put. If 9, you put the 9. So Z for MRR will be equal to, the 9 divided by y bar, this is y star, means 0.99166 divided by 0.2. Log of that one, 9 by that result, that gives 12.94. This is the Z value. This is the Z value for what? This is the Z value for MRR. Similarly, you can find out the Z value for SR. In the same logic. Here you can see we have taken the minimum value for MRR because that is the most acceptable value. And here SR is the most acceptable value. The worst value will be the YG bar or Y bar. Since all the SR values are less than 6, this is the worst value. And YJ, this is the minimum and the minimum value of this one. So this is 3.65 here. Then you've got what is that? 6 here. Log of that one, 9 divided this, you will get this 31 like this. Okay. This is the Z value for SR. Similarly, for ROC, we can calculate the Z value. The objective of Z value, this is to evaluate the constant Z in order to find out the individual utility factor or utility index. Okay. So this Z value we find out by considering the highest value and the lowest value, put a log to this one, and this is the most acceptable value given a weightage of 9. This we get this the Z maximum, Z value for different performances or different responses. This is MRR, SR, and ROC. We are working on the performance or the responses now. Now, this is the weightage given to this. All these, there are 3 responses. Some of these responses should be 1. And overall altimeter, we get these responses as here is equal to 1 by 3, 1 by 3, and 1 by 3 to all the responses. and this the overall utility is calculated. Overall utility is calculated according to that sum of I is equal to 1 to k. There are three, that is even 1, even 2, even 3, like that. That the weightages are given to that one. All equal weightages. It is free to the user that you can give different weightages to different responses depending upon your experience and depending upon your analysis. And this is what you get for different factors. Based on that formula, we calculated Y for MRR, Y for SR, and Y for ROC, and then finally we got the overall utility. Overall utility. And you can see that in experimentation number 18, that is having a parameter setting of A2, B3, C3, and D1, we are getting the maximum utility, overall utility of 7.069. That is the optimum utility. That is the optimum utility we are getting there. Okay. So after calculation of this, what should we say? That we have conducted 27 experiments. In some experiment or by some parameter setting, we got the maximum MRR, minimum SR, and minimum DOC. But here, this one, by calculating the utility of individual parameter, individual responses, combining them together to get the overall utility factor or overall index, we got this, that this is experimentation number 18 gives the overall utility is the maximum. The overall utility is maximum in the parameter setting that we provide in experimentation or experiment number 18. Okay. So here, what are the parameter settings? A2, B3, C3, and D1. And D1, these are the parameter setting. Okay. Now, if you put it in the MRR table, in the SR table, and in the DOC table, you will get different value of the DOC, SR, and MRR. That may not be equal to the maximum value or optimum value we have got. Earlier when you considered it as a single objective problem. But however, if you adopt this, you will get simultaneously all the parameters will be optimized. All the parameters will be optimized. Okay. This is how we get the utility into picture. We get the utility into picture. You can see this one, that in the 18 number here, this is the peak, this is having the maximum value. This is simply a plot of what you have got this 27 experiments, and you get the peak over here. And how to calculate this one? This you can calculate by this. This factor A, this is having 2, factor B having 3, factor C having 3, factor D having 2, like this one. This is rank 1, this is having the maximum deviation, maximum difference. This is affecting the responses. And this second, third, and fourth, we can rank this one. These are the mean utility value for each level. And these are the plots. These are the plots for the level. You can see that's A2, B3, C3, and this is D2. They are giving the higher values or the highest values. And this is the overall utility. Okay. So what we conclude is that utility-based Taguchi method is effective for evaluating the optimal parameter settings. Optimum parameter setting, or we are converting by using a Taguchi method with utility, we are getting a multi-objective optimization scenario. This approach is efficient enough to solve a multi-response optimization problem. Confirmatory test has validated the parameter setting determined the utility with Taguchi method is correct. This validation is done. And then this can be used for continuous quality improvement and offline quality control. Okay. Thank you. And if you got any queries, you can ask.
If you have any queries, you can put it in the chat box. Okay, there is no such queries, only to request for sharing the PPT that will provide. Okay, so on behalf of the participants, let me thank the coordinator, Professor Debadutta Mishra sir, for uh, taking this very interesting session. I hope we all will take something out of this session and we can implement it during our research work or teaching. So that's all for this particular session. The next session will start at 11:30. So I request all to join by 11:15. Thank you for attending this session. We'll start the session at 11:30. Thank you.